understand the ability of the trained model to generalize on new data, to compare also different configurations. For example, if you want just to compare one model with another model that has a different configuration for the hyperparameters, or maybe also compare completely different models, and so that we can choose which performs the best on this specific task. But keep in mind that there's no single machine learning algorithm that is always superior across all problems. So maybe this is called the no free lunch theorem. So you always expect that there is an algorithm that performs very well on specific tasks, that it does very poor on other ones. So you cannot always say, I will use this machine learning is the best one. You just need to train different models and compare the performances. Then I was mentioning earlier that like this fight between underfitting and overfitting. Underfitting is when the model is too simple and you cannot, let's say, understand the pattern that lies behind the data. While overfitting is the opposite, as already mentioned. When you try to train a model, you need to find the good balance between these two aspects. So in order to do that, and for example, try to some hyperparameter tuning in order to find the best, let's say, combination of parameters, hyperparameters, I'm saying, to compute with the actual parameter of the models. To find the best ones, we can manually search them, but of course, it takes ages to find the optimal solution. Otherwise, we can apply grid search. Basically, we define a grid of values. It's almost like an in-course approach. So test all of them. We define grid, and of course, we are guaranteed to find the best combination in this defined grid. But this, of course, as I said, it's a sort of a brute force approach, so it's computationally very expensive. Otherwise, we can have a random search, but we are not guaranteed to find the best value for our model. But also, there are some probabilistic approach, but they are quite hard to implement, let's say, for some basic. Then another method to improve, let's say, the balance between underfitting and overfitting is to use regularization methods. The idea of these methods is basically to add a penalty to the loss function so that the model gets discouraged from becoming too complex or becoming to overfit the data, or on the other hand, to rely too much on a single feature. There are two main regularization methods. The first one called L1 or lasso regression. Basically, add a penalty that is proportional to the absolute value, the coefficient to the partial loss. So in this case, we sort of shrink some coefficient to 0, and we can say that we are performing a sort of feature selection. So we are shrinking some coefficient to 0, so they are basically not relevant anymore to the final output of the. The second method is to have two regularization on range regression. That's a penalty that is proportional to the square of the magnitude of the coefficient. So in this case, we shrink the coefficient towards 0, but never exactly 0. So we reduce the impact of some less important features. So we only we are not in this case deleting some less relevant feature, but we are making them less important in order to make a final evaluation. Another method to improve the outcome of the training is to use cross-validation. This method basically splits the entire data set multiple times to make sure that every data point has a chance to be used for both training and validation. This is an example of k-fold cross-validation. We have 4 folds, So this is our entire original training set. Can decide, for example, the first the first part is used for the validation set in the first iteration, while in the second iteration we use the second one, so on. So basically, we never, we make sure that each data within the original training set is used at least once for either training or validation. There are also some methods that basically combine the prediction from multiple machine learning models to produce a single model that is superior in performance. Two main methods called bagging. In this case, we try to train different independent models, the subset of the original training dataset, and then we try in the end to combine their outputs. One example of bagging is a random forest, which is an ensemble of decision trees that we've seen earlier. The name is quite clear in this case. Then we have another that is called boosting. In this case, we try to sequentially train the models. So each model is trying to correct the model of the preceding, the error of the preceding models. So in the end, we can combine the prediction and have a better outcome. Probably the most famous model to do that is called XGBoost. And we will, you already heard of, maybe you will apply in the future. Here we have a graph representation of the sets, and in the case of bagging, we parallelly train different models, while using boosting, it's a sequential training of different machine learning models. And then the last step, of course, is to use your train model to make predictions. This is also called model inference. We can call this. But I think there are some key points to take into consideration in this case when you should think about this before training a model in theory, but this affects how the predictions are made in the end. So, for example, if you need a model that somebody used for some real-time tasks, it means that it's need really has to do some predictions really fast. So if you use some large models, usually the prediction takes more time, so you cannot use that for real-time applications. Also, my personal experience, I had to, let's say, to take this in mind because we wanted to develop a model that was basically moving some noise real time. Basically, it was the main objective was not even to be the most to reach the most accurate result possible, but to make the kind of compromise between latency and the output. And of course, the model size is also something that you need to take into account. A complex model can be very slow. You need maybe some dedicated machine to run that model. So the smaller the better in this case. And then it also depends when your model will run. For example, it's in the cloud, it's on a sort of embedded system, your mobile phone, and it really depends on your final code. There are also some techniques that basically try to detect if your model is degrading in performance over time. So this is one also. There are many strategies to detect this so-called model drift, and also monitor the performance of your model also after training it. So you can see how it's answering, for example, to some question in the case of a large language model. Yeah, I think I will conclude here because I've introduced many concepts. I think maybe too many, but yeah, this was just an overview to give some basic idea what is machine learning. I did not cover everything. I did not cover also from the mathematical point of view, but this was just an introduction to this topic. Maybe I don't know how many of you already had your master degree. Have any of you already had machine learning courses? 1, 2, 3. No one else?